I was sitting in a cafe in Palo Alto last week with a guy who couldn't stop staring at a digital chart on his iPad. He pointed to two specific numbers, 24 and 18, with a look of pure, unadulterated triumph. "We've already won," he told me, his face lit up with that giddy certainty you only see in true believers. He started scrolling through these incredibly fluid, AI-generated videos of neon landscapes and talking animals, convinced that these pixels were the ironclad proof of a permanent civilizational lead. To him, the intelligence gap was a settled matter of algorithmic elegance and research papers. But then I asked him a simple question. How much did that model improve the defect rate of a steel mill in Ohio this morning? The silence that followed was heavy. He looked at me as if I'd interrupted a symphony to talk about plumbing. He quickly pivoted back to a chatbot that could write sarcastic poetry about the blockchain, obsessed with the soul of the machine and its ability to mimic human wit. He was captivated by what is essentially a digital mirage, the high-resolution surface of a civilization that has prioritized financial arbitrage and social media automation over actual material creation. Meanwhile, halfway across the world, the conversation isn't about poetry or AI personhood. It's about the engineered dividend. It's about the unglamorous work of synchronizing 10,000 robotic arms and optimizing smart grids to the third decimal point. While we celebrate a scoreboard that measures the height of our castles in the air, we're ignoring a decisive shift. The laboratory-to-factory pipeline is being built elsewhere. That instantaneous shift in my companion from fervent pride and a digital score to total confusion when faced with physical reality made me realize something unsettling. That 24 to 18 lead might just be the final flickering inertia of a system that can simulate reality perfectly, but has forgotten how to build it. If we've won the battle for the most eloquent code, why does it feel like we're losing the war for the flesh of modernity?
That story, that cafe conversation, it just perfectly encapsulates the core tension of this whole global AI contest, doesn't it?
It really does.
Because so much of the public conversation, it stays right there on the surface.
Yeah.
It's about how eloquent the chatbot is or the valuation of the newest startup.
Right, the digital mirage.
Exactly. But what our source material shows us today is something much deeper. It's a profound divergence in what the goals even are. We're really looking at two competing civilizational blueprints for what AI is for.
And that's our mission for this deep dive. We want to unpack that central conflict. We're going to try and move beyond the hype, beyond the conversational AI wars, and ask a much harder, more foundational question.
Which is
this global contest really measured by how elegant the code is, how human-like the conversation feels, or is it measured by how efficiently you can turn that code into physical power, into actual material creation?
Yeah, that's the question.
We're going to examine the evidence across four really critical areas. The quality of the data these systems are fed, the trends we see in patents, the underlying industrial strategy, and then the deep supply chain integrations that are, actually shaping the physical world.
It's about who controls the means of production, not just the means of simulation.
Precisely.
It's an investigation that shifts the focus from, let's say, the abstract intelligence being debated in Silicon Valley to the concrete applied intelligence that is right now transforming factory floors and energy grids thousands of miles away.
So let's start right where that anecdote did. Let's unpack this idea of the digital mirage and what the sources call the soft data dilemma.
Sounds good.
So the sources jump right in with this very powerful critique. They call it the laboratory dilemma. And the basic idea is that a lot of the foundational AI prowess in the West, particularly in the US, is becoming, what's the phrase they use, unmoored from the physical world.
Unmoored. That's a great word for it. We built these incredibly powerful, massive foundational models, but when you really look at where they're being applied, it seems to be in a very narrow, very specific set of sectors.
And what are those sectors?
Well, when you analyze where the big venture capital money and maybe more importantly, where the top engineering talent is going, you see this incredible concentration. It's almost all being funneled into two main areas: financial arbitrage and social media automation.
So we have the most expensive, most powerful artificial intelligence ever created, and it's being used to optimize ad clicks.
Optimize ad clicks, generate synthetic content for Instagram, and refine trading algorithms for high-speed, speculative markets. It's all about amplifying virtual value.
So the intelligence is optimizing the flow of money and attention, not the flow of atoms. It's not being applied to material science or grid optimization or physical logistics.
Which makes the AI less of an engine for broad civilizational progress and more of a tool for financial harvesting and attention mining.
It almost sounds like a reflection of the economy it grew up in.
Well, it is. It absolutely speaks to the priorities of the ecosystem. If you're in a highly deindustrialized environment where capital is just overwhelmingly concentrated in finance and digital platforms, where does the top STEM talent go?
It goes where the money is.
It goes where the money is. So the AI that gets built just reflects those priorities. It gets really, really good at optimizing capital flows, but it's not designed to think about improving tangible infrastructure.
Yeah.
The speculative consistently wins out over the substantive.
And this structural bias, this focus on the virtual, it leads directly to a huge difference in what these AIs are eating, for lack of a better word, their data diet.
A data diet, I like that, yes. There's a profound divergence between what some call noise and what they call hard data.
So if your main goal is financial harvesting and attention mining, what are you feeding your models?
You're feeding them the noise of social media. The training data for so many of these large language models, especially the ones trying to predict financial markets, is just dominated by human opinions, digital ephemera, and all the highly subjective emotional content people generate online.
It's messy data.
It's incredibly messy. It's emotional, it's often exaggerated, and sometimes it's deliberately misleading.
And we have some specific numbers on this, right? From reviews of studies that tried to use this data to predict stock prices, which platforms are we talking about here?
The main one, by a huge margin, is X, what used to be Twitter. An overwhelming 65% of the research papers we looked at used X to gather their text data for sentiment analysis.
65%. Why so much focus on one platform?
It's the real-time global nature of it. It's just a fire hose of public opinion. But researchers also use a lot of other sources like StockTwits, LinkedIn, even Yahoo message boards, and Facebook. They're all repositories for this really subjective, often volatile, emotionally charged human reaction.
The whole idea here is based on a kind of faith and sentiment, isn't it? The belief that if you can just measure the collective digital mood, you can profit from it.
It's a huge assumption.
But what happens when you actually test that assumption? When you look for the empirical proof, how effective is all this sentiment data, really?
And this is where that digital mirage you mentioned really starts to shimmer and fade. There's a huge gap here. The heavy reliance on sentiment data exists despite there being minimal empirical proof that it's actually effective in forecasting.
So they're just assuming it works.
For the most part, yes. A major systematic review looking at studies from 2020 to 2024 found that most researchers just assumed the effectiveness of social media sentiment. They built it into their complex models without ever really isolating it to prove its value.
Wait, so they're building these incredibly complex billion-dollar systems on an unproven assumption. That sounds like a colossal strategic error.
It suggests a really deep-seated faith in the predictive power of human emotion, even when that emotion is, being shouted anonymously into the digital void. The review found that only one study did a clean, direct comparison.
Just one?
Just one study that tested stock price prediction with social media sentiment and then tested it again without it.
Okay, so this is the crucial test. What did that one study find? What's the actual tangible value of all this digital noise?
It did find a positive effect, but the improvement in accuracy was, it was strikingly limited.
Oh, limited.
When they incorporated sentiment, the model achieved a 62.2% accuracy rate in predicting stock price movements.
Okay. 62.2%. And without it?
Without the social media data, relying only on traditional financial data and news reports, the accuracy was 60%.
So it's a 2.2% increase.
A 2.2% increase. That's the bump.
That's a remarkably thin foundation for an entire pillar of AI development, one that's consuming billions in infrastructure and talent. If the gain is that marginal, doesn't it just call the whole strategy into question?
It absolutely raises profound questions about resource allocation. You have the most advanced machine learning models being deployed, models specifically optimized to handle this messy, noisy data, all to extract what is, at best, a marginal gain.
Can you talk a bit more about that? What kind of technical power does it take just to make sense of this noisy data?
Well, the researchers primarily rely on these very sophisticated deep learning models. Most commonly, they use something called long short-term memory networks, or LSTMs.
LSTMs?
Right. They're part of the recurrent neural network family. They were the most used approach in the papers we reviewed. And they're used because they're specifically designed to understand context and dependencies over long sequences of data, like a social media feed. Human language is full of nuance, sarcasm, context.
Yeah.
It's hard for a machine to parse.
So you need the most complex neural networks just to get a tiny bit of signal out of all that human noise.
Precisely. You also see them using specialized transformer-based models, like something called FinBERT, which is a version of a huge language model that's been fine-tuned for financial text. They need this immense capacity just to deal with the messy, subjective content from users on X. The engineering effort is massive because the data itself is just low quality.
It really sounds like we're spending the GDP of a small country to solve a 2.2% problem that, at the end of the day, just accelerates capital flows. It's a strategic cul-de-sac.
And if your AI is trained on data with questionable predictive power, it risks becoming a tool that just amplifies financial volatility instead of generating real economic capacity. This brings us to a stark contrast when we shift from the soft sentiment data to the hard quantitative metrics of patents. This data quality problem leads directly to a divergence in innovation philosophy.
Okay, let's make that pivot. From the soft, emotional data of social media to the hard, legal metrics of innovation. Patents. Because patent filings, they're much more than just legal documents, right? They're clear strategic signals of where a nation is placing its long-term bets.
And when we look at the numbers, it's a story of two completely different mindsets clashing head-on. It's what the sources are calling China's volume strategy versus the U.S.'s depth strategy.
So let's start with the volume. China's approach is described as a massive state-led innovation engine. How overwhelming is it in pure numbers, especially for something like generative AI?
The scale is just staggering. It really is. And it's clearly the result of deliberate national intent. Between 2014 and 2023, China accounted for over 70% of all global generative AI patents filed.
Over 70%.
Yes. And if you look at the yearly trend, it's even more dramatic. In 2019, China filed about 59,000 AI patent applications. By 2024, that number had peaked at nearly 189,000.
Wow, so it more than tripled in just 5 years.
More than tripled. It's a reflection of an overwhelming ambition to just blanket the entire technological map.
But that raises the obvious question, doesn't it? If you're filing almost 190,000 patents in a single year, how can you maintain quality? Is the U.S., with this depth strategy, actually securing the more valuable foundational innovations in the long run?
That is the perfect question, because the U.S. strategy is almost the mirror image. It intentionally sacrifices volume for what it hopes is quality and long-term relevance. While China's numbers were surging, U.S. filings stayed very stable, somewhere between 31,000 and 35,000 each year.
So on paper, it looks like the U.S. is falling behind.
It does. But the quality metrics tell a different story.
And what defines a quality patent in this context? What makes one more valuable than another?
The key metric is something called forward citations. This is a measure of how many subsequent patents and research papers cite a particular patent as foundational to their own work.
So it's a measure of influence.
It's a direct measure of influence and foundational importance. And U.S. patents, despite their lower volume, have significantly more forward citations. This is what positions the U.S. as the gold standard for foundational innovation. It allows them to effectively collect technological rent from future breakthroughs around the world.
So it's about owning the core ideas.
Owning the core ideas and also focusing on patents with staying power. The U.S. has a slightly higher proportion of active patents, 88% versus 87% for China. It's a small difference, but it indicates a strategic focus on filings with enduring value, not just filing for the sake of volume.
So China is trying to dominate the entire field right now by covering every possible application, while the U.S. is trying to own the underlying operating system of AI, which would give it long-term leverage.
That's the divergence in a nutshell. One strategy is about scope and immediate application. The other is about foundational control. And you can see this in the focus areas. China's volume is broad, it's tactical, it covers voice tech, computer vision, automation things that translate directly into industrial output.
And it's very domestically focused.
Very. In 2023, China filed 1.64 million patents overall, which is almost half of all global filings. But only about 7% of those were filed internationally. They were building the AI powerhouse at home first.
Let's get into the companies driving this, because the difference here is maybe the most telling part of the whole story. Who's leading the charge in the U.S.?
The U.S. leaders are who you'd expect, the established titans of the digital world. IBM, Google, and Microsoft. IBM has the most historical filings with over 10,000, showing its long-term investment. Google and Microsoft are driving the current breakthroughs in generative AI and machine learning frameworks.
And it's mostly software and cloud-based.
Largely, yes. It's software, enterprise services, foundational models. It is interesting to note that Samsung, a non-U.S. company, is actually second in U.S. filings, which shows its huge role in AI hardware and consumer electronics within the American market.
Okay. Now, Compare that list of U.S. leaders to the top of the Chinese filing list. The contrast is, well, it's immediate.
It's immediate and it's definitive. The list is absolutely commanded by an entity that is not a software company or an internet company. It's the State Grid Corporation of China.
The national power utility.
The National Power Utility. They have an astonishing 26,309 filings. That's more than double IBM's total. It just dwarfs everyone else. After them, you have the big tech players like Tencent and Baidu, but State Grid's dominance tells you everything about the national priority. For China, AI is inseparable from critical infrastructure. It's about energy.
26,000 patents held by a power company. That's a jarring contrast to Google or Microsoft. This isn't about search algorithms or office software. This is about lighting cities and powering factories.
It speaks to a core national belief that AI's primary use is to enhance physical control over essential resources. It's a very clear strategic choice. And while U.S. firms are actually refining their portfolios, you see IBM's filings dip to just 681 in 2023, a signal they're focusing on high-value, research-oriented AI. The Chinese firms are consistently ramping up, driven by government policies like Made in China 2025.
So this U.S. consolidation, this move toward depth, could be seen as a smart strategic move, but you could also see it as a retreat from broad industrial application, couldn't you? It's a calculated risk. The bet is that by owning the foundational models and the core cloud infrastructure, which we'll get to later, they'll capture the most value, no matter who files the application patents. They want to be the indispensable AI engine.
But the risk is?
The risk is that the sheer volume and focus of the Chinese filings, especially in areas like automation and energy, suggests they're building an entire parallel technological ecosystem, one that's fully vertically integrated and might, over time, become less and less dependent on U.S. foundational software, which brings us perfectly to the application side of this, the tangible physical results of this industrial focus.
Exactly. If the West is focused on the digital ghost, the elegant code and the financial abstractions, then the East Asian focus is all on the flesh of modernity. We're talking about massive vertical integration, AI plus manufacturing, AI plus agriculture, AI plus energy.
The entire philosophy is different. The metric for whether an AI is useful is brutally simple. Can it measurably improve yield? Can it reduce the defect rate? Can it optimize logistics? If it can't, it's just a digital mirage. It's worthless. AI as a tool for physical production.
Solely as a means to elevate physical production and national capacity. The final output has to be atoms moved, not just pixels simulated.
And the sources have a perfect little story that illustrates this almost instantaneous jump from a lab breakthrough to the factory floor. It highlights the ruthless efficiency of what they call the laboratory to factory pipeline. Tell us about Lao Chen.
Right, Lao Chen. He is a production manager at a high-precision component factory. So his world isn't about chatbots that write poetry. It's about microscopic physical reality. And for years, his factory had this persistent, expensive, and really boring problem.
Boring problems are often the most expensive ones.
They are. It was a chronic 3% defect rate in high-speed microscopic welding. Now, 3% doesn't sound like a lot, but it was costing the company millions every year in wasted material and rework.
A real tangible economic drain. So how do they use AI to solve this?
Instead of waiting for some general AI breakthrough from a lab halfway around the world, Lao Chen's in-house engineering team integrated a very narrow, very specific vertical AI model right onto their assembly line. It was a computer vision model.
And it wasn't asked to predict the stock market?
No, it was trained on one thing, the minute thermal signatures and visual patterns of their welding process.
And what was the impact, the measurable physical impact?
The AI quickly learned not just to spot errors after they happened, but to predict machine wear and component drift before they caused a defect. And here's the key part of the story. The patent for this specific algorithm, this little industrial breakthrough, it didn't just sit in a university database for a decade. It was coded, converted, and fully implemented into the control software of the robotic arms on the factory floor by the end of that quarter.
By the end of the quarter, a patent is converted into a moving robotic arm in 3 months. That speed. That's the real competitive advantage, isn't it?
It is. It's not just the sophistication of the code, it's the institutional speed at which that code starts moving physical atoms and solving expensive real-world problems.
The whole system is aligned to prioritize the immediate physical utility of the algorithm.
Exactly. The factory, the engineers, the legal system.
Yeah.
Everything is geared for rapid implementation. And this difference in priority is reflected in where they direct their best people. their human capital. The sources call it the engineer dividend.
Right, the flow of talent. It's a huge indicator of what a civilization values. So in the West, where does the top STEM talent tend to end up?
It's systematically siphoned into the abstract and the speculative. Financial modeling, high-frequency trading, and probably most of all, optimizing social media platforms for the attention economy.
So they're optimizing existing capital flows, not creating new physical capacity.
That's a great way to put it. And it contrasts so sharply with the strategic deployment of talent you see elsewhere. Let's look at the other side of that coin, the story of Xiaowang. So you have the Western engineer who's fine-tuning an AI to maximize user engagement on a social media app, a task dictated by the attention economy. Now, contrast that with Xiaowang. He's a top engineer who gets funneled into a state-backed smart grid project.
So a totally different mission.
A completely different mission. His job is to use AI to manage these incredibly complex, millisecond perfect energy fluctuations across a power grid for an entire province, an area that might have the population of a large European country.
So one engineer is trying to get you to click on an ad, and Xiaowang is literally keeping the lights on for 100 million people. He's at the control center of the civilization's nervous system.
Precisely. That cohort of engineers is dedicated to physical construction, to foundational energy management, to national capacity. That's the engineer dividend. It's not just having brilliant engineers, it's making sure they're working on scaling energy efficiency and physical infrastructure for the entire country. That focus creates resilience.
And the success of that hard tech hegemony depends completely on the quality of data they're feeding these models. This gets us back to the data diet, the hard data advantage.
Yes. This is where the divergence from that 2.2% sentiment bump becomes crystal clear. Think about the AI running that massive automated container port in Qingdao. It is not being fed human opinions.
What is it being fed?
Billions of clean, precise data points, the exact weight of every container, instantaneous wind speed and tidal force measurements, the thermal signature from every crane motor, millisecond perfect timing logs for every single movement.
The sources describe this data as unfakeable reality.
That's the perfect term for it. Unlike social media data, which is just distorted by ego, bias, and manipulation, this industrial data is a cold, hard, clean reflection of physical reality. It's specific, it's reliable, and its only goal is to maximize physical productivity. If the long-term race is about resilience and productivity, the AI fed on this hard, clean data is going to win.
And we can see this industrial focus again if we go back and look at the patent data in more detail, right? Beyond just the volume.
The detailed breakdown confirms it. It shows a deliberate, strategic move to wire AI directly into the country's physical infrastructure. So yes, China invests heavily in foundational learning techniques, over 157,000 filings there. But it's the other categories that are so revealing.
Which industrial categories show where this hard data is being turned into intellectual property?
Well, two categories really define the strategy. First is training data generation, which has almost 75,000 filings.
Training data generation. So that's AI that creates data for other AIs.
Exactly. It's a closed-loop system.
Yeah.
They're using AI to automatically generate synthetic, clean data for their industrial models. It shows they're solving the data quality problem internally, eliminating the need for messy human input.
That's a huge infrastructural advantage. They're automating the creation of their high-quality data. What's the second big category?
Powertrain control systems. Over 58,000 filings. This is the direct link between the algorithm and the heavy machinery. It's AI that manages the precise speed, torque, and power delivery for massive industrial equipment. Port cranes, factory robots, high-speed trains.
And optimizing that saves energy, reduces wear and tear.
And maximizes operational uptime. So when you look at these massive investments in automated data generation, in powertrain control, in smart manufacturing systems, the signal is unmistakable. AI isn't an accessory. It's the structural wiring of their national infrastructure.
Which is how they plan to achieve hard tech hegemony, by embedding intelligence into every single physical process.
Right.
But the kind of scale and coordination you need for this, for State Grid to file 26,000 patents, for Lao Chen's factory to innovate that quickly, that can't happen spontaneously in a decentralized, free market system. This brings us to the political and structural context that makes it possible, the developmental state model.
Yes, the developmental state model is the framework that allows for this kind of strategic coordination. It's defined as a state that is intensely focused on economic development and takes all necessary policy measures to achieve that goal.
Which is a contrast to the what these sources call the purely regulatory state model.
Exactly. A regulatory state primarily sets rules, enforces standards, and intervenes when there are market failures. It doesn't typically dictate industrial direction.
So how does a developmental state operate in practice to achieve something like a nationwide smart grid?
Through direct industrial policies, the state actively promotes specific new industries. It mobilizes capital into the sectors it believes will have the maximum spillover effect for the whole society. And, crucially, it mandates close cooperation between the state and major industries. This creates a stable macroeconomy and allows them to execute these very long-term visions.
So it's about providing long-term guidance and resisting short-term financial pressures that might derail a 20-year plan.
Absolutely. The model's power is its institutional capacity. It has the organization and the power to execute these plans and resist the narrow interests of any one company. We've seen similar models used in the rapid industrialization of places like Japan, South Korea, and Singapore.
And in the context of AI, this model ensures that the engineer dividend, all that top talent, gets funneled into projects deemed essential for national capacity.
Like energy and manufacturing optimization, rather than just maximizing short-term shareholder value.
Oh, why, regardless of which blueprint you follow, whether it's the digital Mirage or the physical system, both are fundamentally limited by the hardware, by the physical infrastructure. So we have to talk about the deep supply chain and the upstream bottleneck. Who controls the atoms that do the calculations?
This is where it all comes back to physical reality. The hardware defines the absolute limits of any AI strategy, and that supply chain is characterized by extreme concentration at the top. We're talking about choke points that create de facto monopolies.
And there are three core technologies that basically dictate who gets to compete at the frontier, right?
Three core technologies. First, you have ASML, the Dutch company that has a total monopoly on extreme ultraviolet, or EUV, lithography machines. Without those, you cannot etch the most advanced chips.
Okay, that's one.
Second, you have TSMC in Taiwan and Samsung in South Korea. They are the only two foundries capable of mass-producing the most advanced AI accelerators, the 3-nanometer and soon 2-nanometer chips.
And the third?
Third is NVIDIA, which dominates the GPU market with over 80% market share, plus a few proprietary chips like Google's DPUs. If you don't have reliable access to those three things, EUV, advanced fabrication, and specialized accelerators, you are effectively shut out of the frontier AI race.
Let's dig into that first choke point, ASML and EUV. Why was this such a massive technological hurdle? And how did it lead to this fascinating thing called the ASML Alliance?
EUV lithography is just an immense technical challenge. You're using extreme ultraviolet light to etch features onto silicon that are just a few atoms wide. The light is so easily absorbed, you need a near-perfect vacuum. The light source itself is incredibly complex. It cost billions and billions to develop.
And the problem for ASML was that they had to bear all that risk and cost up front.
Exactly. They face all the R&D risk, but the immediate financial benefits of the smaller, more powerful chips went downstream to their customers, the chip fabricators like Intel, TSMC, and Samsung.
So the fabs needed the tech to keep Moore's law going, but ASML couldn't afford to develop it alone.
It was a shared technological necessity. So, to solve this, ASML did something brilliant in 2012. They created a unique vertical alliance. They offered their three biggest customers a combined stake of 23% in ASML itself.
They let their customers buy into the company.
Yes. Intel bought a 15% stake and committed over 800 million euros to R&D. TSMC bought a 5% stake, Samsung a 3% stake, and both made similar R&D commitments.
That's an amazing model. It's vertical integration without an acquisition. It's a shared bet on the future of physics.
It was what was necessary to sustain Moore's law. This deep collaboration meant the customers got early access to the tech and had influence over its development. It solved the risk problem and secured the entire industry's future.
Securing the physical bottlenecks is everything. Now let's pivot back to the West and look at the parallel supply chain fight there, the compute race among the big tech companies.
Downstream, the fight is all about access to compute. These specialized AI accelerators are a rivalrous and excludable resource, and supply is constrained. Training frontier models requires immense scale, and that scale is dominated by the big cloud providers, AWS, Microsoft Azure, and Google Cloud.
And since they can't just go out and buy TSMC or ASML, their strategy has to be different.
Right. Their strategy is quasi-vertical integration through strategic partnerships with the AI labs themselves. It looks less like a free market and more like a race to corner the available compute through these big alliances.
And we see three major examples of this, right? These interlocking partnerships.
We do. First, you have the Microsoft and OpenAI relationship. Microsoft has been OpenAI's sole cloud provider since 2019. But the big move was the $10 billion investment in 2023. In return for that, Microsoft got exclusive access to the parameters of the advanced GPT models.
Which means they can integrate the best frontier models directly into their own products, all running on their Azure cloud.
It builds their entire AI ecosystem around that priority pipeline. And then you have Alphabet, or Google, which took a multi-pronged approach.
What did they do?
They pursued deep internal integration. They own DeepMind, which they bought back in 2014, so that's an internal unit. But they also invested $300 million in Anthropic, a key competitor to OpenAI.
And Anthropic uses Google Cloud.
Anthropic uses Google Cloud and, crucially, Google's own proprietary chips, the tensor processing units, or TPUs.
So that's the control mechanism. Google designs its own specialized hardware, but the only way to use it is through Google Cloud.
It's a perfect mechanism for vertical control. It ensures that any lab wanting to use their leading-edge hardware has to operate inside the Google ecosystem.
And finally, Amazon is doing the same thing, also with Anthropic.
The same pattern. Amazon has a huge partnership where Anthropic's Claude model runs on AWS. But the key move was Amazon's investment of up to $4 billion to bolster Claude's development, with the condition that Anthropic uses AWS and Amazon's own specialized chips, Trainium and Inferentia.
So the goal for all of them is the same: secure, dedicated access to constrained compute resources for these massive training runs. It's a balance between the hyper-specialized AI labs and the massive hardware capacity of the cloud giants.
It's the Western equivalent of centralizing a critical resource. The market structure favors this conglomerate, quasi-vertical model. It manages the supply chain constraint while letting the AI labs stay semi-autonomous. It secures control over the vital compute resource.
So when we pull the lens back and look at the whole picture, you can really see the two clashing strategies.
The full divergence.
We started with the digital Mirage, this sophisticated AI ecosystem that's perfecting simulation, perfecting financial abstraction, and analyzing social sentiment. And it's doing this based on data that's only proven to give a tiny 2.2% bump in accuracy, requiring immense technical effort just to process the noise.
And that stands in stark contrast to the opposing blueprint, the applied explosion. A strategic focus on building the body of modernity through industrial reality, aiming for hard-tech hegemony by using their engineered dividend to solve physical, unglamorous problems.
Turning the digital into the material through high-speed pattern conversion and hard data analysis. The conclusion seems to be that the future won't just belong to the architects of the most elegant code, the people debating the aesthetics of algorithms. It will belong to the engineers who successfully embed that intelligence into the unyielding ground of industrial reality.
It will belong to the civilization that controls the most efficient, resilient, and intelligent means of physical production, from the energy grid of State Grid to the factory floor of Laotian.
So the decisive shift, the thing we should all be watching, is the speed and maturity of that laboratory to factory pipeline.
That's where the real race is being run.